Hello, this is my talk on coboundary and cosystolic extension from strong symmetry. This is the joint work with Tali Kaufman from Bar-Ilan University. And what I'll talk about today, what our work is about, is coboundary or cosystolic expansion. And these notions, which will be defined later, are high-dimensional generalization of the Chigger constant for graphs. So before our work, it was an open question, or it was a challenge to construct such high-dimensional expanders in an elementary way. So basically, we want bounded degree cosystolic expanders, whatever that means, to be defined later. And there were known constructions, but they all use some heavy-duty machinery from representation theory and or from Burotitz buildings and stuff like that. And what we did is that we already had a construction, an elementary construction for a different type of high-dimensional expansion called the local spectral expansion, which is the analog of the spectral gap. And this work is showing that the examples, the elementary examples we had in that paper, in the previous paper for spectral gaps or high-dimensional spectral gaps, are actually also examples of higher dimensional cosystolic expanders. So the important point, or one of the important points in the argument, is that our construction is highly symmetric, and we are able to exploit this symmetry in order to deduce this bound on these high dimensional Chigger constants. And let me give the definition. So let's start with the classical thing. A finite graph, a finite connected graph, I want to define the Chigger constant. So for a subset of vertices, I define the cut set to be of the set S to be all the edges with one vertex in S and one vertex in the complement of S. And let me define the Chigger constant in some slightly non-orthodox way. I define the Chigger constant as going over all the sets of edges that come from cut sets, and then seeing what's the smallest set of vertices that the set of edges W is a cut set of. So note that if I have a set S and its complement, they have the same cut set. And if I demand that the graph is connected, that's basically the only possibility. If you have two sets, which is you have S and another set S prime, and S prime is not S and not its complement, if the graph is connected, then they won't have the same cut. So if you assume the graph is connected, this is the usual definition. And what we will study is high-dimensional generalization of this constant for high-dimensional generalization of graphs, which are simplicial complexes. So what are simplicial complexes? Let me start with the abstract definition as a set system. So a d-dimensional simplicial complex X is defined as follows. It's a set system over a set of vertices S, and for each k between -1 and d or dimension, k simplices are basically subsets of our set of vertices of size k plus 1. And we don't take all the sets, we take some sets. And the simplicial complex X is this entire set system, but I need one more condition to make it a simplicial complex. And the extra condition is that if I have a K simplex here, and I have a subset of it, so this is some vertices, and this is a subset of some vertices, then the subset is also in X. So it's also in my set system. And in that case, I denote all the K, say this is K plus 5-dimensional, sigma is K plus 5-dimensional, and I can denote all its K faces by sigma K. But I like to think about it geometrically, and geometrically, simplicial complex is gluing edges and vertices and triangles and pyramids and whatever. So the idea is, so here's a 2-dimensional simplicial complex. Each triangle, each blue triangle represents a 2-dimensional face. So think of the subset of these 3 vertices. This gives you a triangle. And the condition is that if I have this triangle, I also have all these edges. Because if I have the set of these 3 vertices, I also have the sets of each of 2 vertices. And so you can think of 1-dimensional faces or 1-dimensional simplices as edges, and 0-dimensional faces as vertices, and 2-dimensional vertices as triangles, and 3-dimensional faces as pyramids, and so on and so forth. So that's the geometric interpretation. And now I want to define what a cut is, a cut set of a set of now K simplices. And I define it in a very similar way. The cut set, so if I take S to be some set of K simplices, so the cut set of S, delta, what I'll denote delta S, is all the K plus 1 simplices that meet our set S in an odd number of K simplices. So what do I mean? So here is my set S. S is the set of these 2 edges. So what is the cut set? I need all the triangles that meet this set S in an odd number of edges. So this triangle will not be in my cut set because it meets the set S twice. So that 2 is even, so it's not in the cut set. This triangle will be in the cut set since it meets this set S only at this edge, so it meets the set S only once, so it is in the cut set, and so on and so forth. So you can see that the cut set of this set of edges S is exactly these 2 triangles. And the kth Chigger constant is defined in a similar way as before. So I look at the sets W of dimension of faces of simplexes of dimension K plus 1, which are cut sets, which come from cut sets and of 1-dimensional lower. And I look at the ratio, how large a cut set could be compared to the set which it originated, and I need some weight. So this is the size is accounting from some degrees. And the fact is that, like in a graph where I always have the empty set as a cut set, because if I take the set of all vertices, then its cut set is just the empty set, since every edge sees exactly 2 vertices. So a generalization of this fact is, if I go 1 degree lower and take some set of K minus 1 faces and take its cut set, and then this is a set of K faces, and then I take this, its cut set, I always end up with the empty set. So there is always the empty set coming trivially from below, from 2 degrees below, but basically coboundary expansion, which I define now, is basically this is, so what is coboundary expansion? So I have a 2-dimensional simplicial complex, and I call it ecoboundary expander. First, if the Chigger constant is epsilon, not epsilon, if the Chigger constant is bounded from below with epsilon, and second, you cannot have a cut set, or the only option for a cut set to be the empty set is that if it comes from 1 degree lower. The only cut sets that the only sets of K simplices which gives you cut sets that are empty are exactly the coming from 1 degree lower. So this is like the demand in graphs that I have only one connected component. And cosystolic expansion is a relaxation of this, is saying again that I have bound on the Chigger constant. And here, the second condition is that if I have a set which its cut set is the empty set, and it doesn't come from below, then it should be large. So you can think about it in the one-dimensional case. This is like saying, okay, I have a graph with several connected components. Each connected component has a good Chigger constant, has at least an epsilon Chigger constant, and all the connected components are large. So it's a weakening of being an expander is having large connected components, and each one of them is a good expander. So that's the cosystolic expansion. And the problem is with constructing examples for this, for cosystolic expansion or for Coboundary expansion, is that in high dimension, when we're not dealing with graphs, we don't have the Chigger inequality, meaning we can't get these Coboundary or cosystolic expansion out of spectral properties, out of the spectral gap, or out of analyzing the random walk. We need some different machinery. Okay. So what are some applications? I will not go over them. But why do we care about cosystolic expansion? So first, Kaufman and Lubotsky showed that you can get locally testable code out of them, and Kaufman, Evra, Kaufman, and Zemmer, or Kaufman and Tesler showed that you can get actually quantum LDPC codes, and there are some other implications for something called the Gromov topological overlapping property, and so on and so forth. I will not cover everything. And what was known before this work, so in one dimension, everything is easy because you do have a Chigger inequality. So basically, family of expander graphs are bound on Chigger on the Chigger constant, and by now several constructions are known. But in high dimensional cases, we are a little stuck because random things do not work. They do not give you bounded degree cosystolic expansion. And known examples are, as I said earlier, require a little heavy duty machinery. You need the theory of Ramanujan complexes and so on and so forth, and that's non-elementary. And as I said earlier, now this lecture is about how do we prove that a construction we had, which is already elementary, gives you cosystolic expansion. Okay, so to see how we get cosystolic expansion, I need to define something else. I want to define something called a link in a simplicial complex. So say X is a simplicial complex and tau is some simplex. The link of tau is a subcomplex of X, meaning it's also a simplicial complex, defined as all the simplices in X that do not intersect tau, but if you take a union, they are a simplex in X. So it looks a little scary, but a picture again is worth 1,000 words. So if this is X, this is my simplicial complex X with the triangles and all, and this is my vertex, and I want to discuss the link of this vertex. So I need to take all the simplices which do not intersect this vertex. So V is not a vertex in them, but that complete it to a simplex in X. So this edge is an example. It doesn't have this vertex, but if you look at this set of 3 vertices, it is in X. So what you get in the link of the vertex V is basically what you should think about as like the small sphere around V. So the link in this drawing, the link is this, just this hexagon. And Kaufman Kaufman told us how to deduce a cosystolic expansion. And what they said that if you start with a d-dimensional simplicial complex and the links are coboundary expanders and the simplicial complex has good spectral properties, whatever that means, then you can get cosystolic expansion. So you needed the links of being coboundary expanders. It's a local condition on the links. And the spectral expansion is also, well, it's a global condition, but it can be deduced locally. And these two gives you a global thing of a cosystolic expansion. But it seems that we didn't get very far because we still need to know that the links are coboundary expanders, which is again a challenge. So what are some examples of coboundary expanders? So I think one of the first results is if you take a single d-dimensional simplex, one simplex, and take it as a complex, all its subfaces, then this will have a good coboundary expansion, but that's just one object, that is one simplex. And Gromov showed that you can take simplicial complexes called spherical buildings, and those are coboundary expanders. And Lubotsky, Meshulam, and Moses generalized Gromov's work to building-like complexes, so stuff that looks like spherical buildings or shares some properties. And in both Gromov's or the LLM results, what is heavily used is the symmetry. And our idea was to bring forth this use and to understand it. So now I want to start with the classical result. How does symmetry helps us when we are trying to bound a Chigger constant? So let me call a graph strongly symmetric if there is a group of graph automorphisms that each edge can be translated by this group to each other edge. So for instance, this graph is strongly symmetric because you have the group of rotations acting on it. So you can, if you have this edge, you can rotate it to that edge or to any other edge. This graph is not strongly symmetric because you don't have, if you look at the symmetry group, you don't have a automorphism of this graph that takes this edge to that edge, obviously. And a classical theorem that if we start with a graph which is strongly symmetric, then the Chigger constant of this graph is 1 over twice the radius of the graph. So the radius of the graph here is the usual thing. You have 2 vertices, you can count what's the distance between them, what's the graph distance, and the radius is just this maximal thing. If I take one vertex, what's the vertex with the smallest distance to each one of the vertices, the other vertices, and that's the radius. So you can, if you have a symmetry and bounded radius, you can bound the Chigger constant. And what we did, or the first result we have, is that you can actually do this idea in higher dimension. So if you define the k-dimensional radius in the correct way, which is not trivial, and you assume strong symmetry of the simplicial complex, then you can get a bound on the coboundary expansion. You can prove coboundary expansion from strong symmetry and a bound of radius. But now we are at a different problem, that bounding the radius, again, the k-dimensional radius is again problematic. It's not easy. But another thing we found out, that was the second revelation of this project, was that if we have two-dimensional strongly symmetric complex, then it has a symmetry group acting on it, and we can actually read or bound this high-dimensional radius by studying properties of the symmetry group, presentation theoretic properties, namely for the experts, by bounding the Dehn function. And now we have like a technical tool of studying the group and not studying the simplicial complex. And now applying all this machinery to our examples. So we had this 2018 elementary construction of spectral high-dimensional expanders, and an additional feature that they were extremely symmetric. All the links were super symmetric and everything worked, so symmetry was not a problem. And we have this machinery that if we apply everything and we study the groups, we can deduce local coboundary expansion, namely show that links of vertices are local coboundary expanders, and then hit it with the Kaufman-Izhar theorem and prove that they are in fact, they give new examples of bounded degree cosystolic expanders. And that's what I describe here. So that's the last slide. So you start with a three-dimensional complex in our construction. Izhar and Kaufman tell you you need spectral expansion, which we already know, and coboundary expansion in the links of vertices, and then you get cosystolic expansion. But we already have spectral expansion, and all we need is coboundary expansion in the links. And the links are strongly symmetric, so we need to bound the high-dimensional radii. And this is done because we know intimately the symmetry groups of the vertices, so we are able to study them and then bound their Dehn function, and then deduce the bound on the radii, and the bound on the radii gives you local coboundary expansion, and that gives you global cosystolic expansion. So I don't have time to describe those examples, but those are basically our 2018 stock paper elementary constructions, so you can read it there. Okay, thank you.